Hello, welcome to our presentation. We are Learning Storage Networks. My name is Rohit Bulanani.
I'm Jack Hornbuckle, or John.
My name's Joseph.
Oh, Rahul, you're muted too.
My name is Rahul. I'm sorry for that.
Name is Remy or Parpina.
I'm Daniel.
Okay. So we want to start off with a little bit of context. So why learning storage networks? In modern times, technological use has exploded, and there's a growing need to store all the data that comes along with this development. Hewlett-Packard Enterprises offers its clients large-scale storage systems for this purpose. These storage systems are connected to HPE's clients and other storage devices through what are known as storage area networks, or SANs, which allows for large-scale analysis and communication of data. So the main reason for using storage area networks is to create an exclusive high-speed channel for sending and receiving data from a storage device. If data has to move from a client device, as can be seen from the image, it must pass through the switch, which then sends that information to the appropriate storage device, and vice versa. However, this diagram only shows one possible structure for a SAN. There could be thousands of clients and servers connected by an equal number of switches at any given time. HPE has many clients which are large-scale businesses on their own. In order to provide adequately, HPE has to set up an enormous number of networks in order to support this. So considering the massive scale at which HPE and its clients operate, the current status quo of just waiting for an issue to arise and then handling it is unfeasible. Sometimes there are anomalous readings which occur in the gathered data, which could point to a deeper issue in the SAN or the storage arrays. In order to capture and predict future anomalies like this, learning storage networks comes into play. Furthermore, once these possible issues are detected, a company engineer can be alerted to investigate the anomaly further. Detecting and predicting outliers allows for proactive prevention of these underlying issues in the hardware or software, saving an enormous amount of time and money for companies which might have been wasted trying to find and deal with these issues.
The issues we hope to resolve includes a slow and resource-heavy protocol. Since it is difficult to pinpoint a problem, we are hoping to use machine learning to help try to troubleshoot a protocol instead of having the ticket being passed among multiple teams. Since currently HPE does not have automated error detection and they have to wait until a client complains or an error becomes critical, we hope to help anticipate the issue before it happens and by monitoring the switches and the information that passes through them, so we can detect abnormal behavior and issue a warning to the appropriate team, so it wouldn't have to be passed around many times. We decided to split our project into phases for us to complete. So the first phase would be to collect and structure the switch data, so we would be able to feed it to the machine learning model. And the second would be for our model to be able to accurately predict outliers. And the last goal would be to send automated notifications to the engineers, whether that be by email or by notification. And our goal for the project would be to have a machine learning model that is accurately able to predict and troubleshoot where the issues are stemming from.
All right, so as a high-level overview of how we approached solving these phases, if you look at the first layer, you could see the switches and the storage area networks. And those switches are all basically sending the data that we are collecting. And then in the second layer, in the data collection phase, we have scripts, which we then use to collect data from these Brocade switches and then store on a server. And then once we have a server composed of a bunch of raw data, enough to train a machine learning model, we then use tools like Pandas, Python, Keras in order to feed that raw data after cleaning it to our machine learning model. And after that, we have a trained machine learning model completing phase 2, which then can be used to notify the engineers in phase 3.
So because the project focuses around data collection analysis, the flow of data could potentially be large. Software needs to be scalable from the start. Furthermore, the actual hardware being tracked with error data is expensive. It's not acceptable for the software to make mistakes when collecting or analyzing sensor output. As a result, the software must be simple, easily traced, easily maintainable, and consistent. So our choices for tools for collecting data off these switches came down to Pifos or Paramiko. Pifos is a library of REST API bindings officially created and supported by Brocade, which is the fiber channel switch manufacturer. And REST is a protocol that uses HTTP to send requests for data, with the script treating the switch as if it was querying a website. It scales better than Paramiko, and it's updated alongside switch firmware, so the official support is better going forward. Paramiko, on the other hand, is an SSH library that allows our script to log into a remote terminal to execute commands directly on the switch, and then receive data back as plain text. This, however, means we'd also have to write, potentially support our own text parsers in the future. Because the data collection off the switch is meant for terminal use by a human, the priority there is human readability and not computer usability.
So as specified, one of the decision problems that we faced early in the project was to choose amongst Pifos and Paramiko. The image shown on the screen shows some sample data using Pifos. Using Pifos, we got JSON structured data in key value forms. Though it may not be very convenient to read and understand from a layman's perspective, for us as engineers, it makes it very convenient to extract essential information using this format. Next slide. On the other hand, when we were using Paramiko, the sample output looked very well structured and readable. However, extracting the data from this text file is very code intensive. So in order to come to a solution, we had to weigh the advantages and the disadvantages of both these libraries. Next slide. Since Pifos is managed by Brocade, it is scalable and it automatically updates with newer firmware versions. The data is JSON structured and it's easier to parse it. And we have access to more useful utilities for format conversions and parsing. However, the documentation for Pifos is not well written. We cannot collect data for all the functions since Pifos is a relatively newer library and does not support all the functions at the moment. Also, we cannot collect data for the older switches since they do not support the REST API features on which this library is based. Paramiko, on the other hand, is very easily accessible and we can directly call the command line functions without having special documentation knowledge and is supported by all the switches. However, the data is not very well structured for parsing, and since Paramiko relies on command line functions, the code needs to be manually updated every time the switches update. So our solution, next slide. So our solution actually involved using both of these libraries, depending on the shown decision process. If the switch does not have a firmware version supported by Pifos, we just use Paramiko. Otherwise, we would divide the functions on the switch in terms of their availability in the Pifos library. Next slide.
All right, so now that basically comprised the first phase of our approach to solving the issue of error detection on the switches, and now moving on to the second phase of trying to train a machine learning model. After collecting all that data, we had binary labeled data. And since this data was labeled, this is something called a supervised learning task in the machine learning. And so since our data was labeled as in binary format, we decided to go with a support vector machine, or an SVM, in order to try and classify whether the switch was in a state of normalcy or whether it was an outlier state. And then we also wanted to make use of something called a long short-term memory model, or in other words, an LSTM, because LSTMs are very good with sequential time series data. And the data we were pulling from the switches was in time series format, so we thought to give LSTM a try. All right, so now looking at the architecture of both SVM and LSTM, this picture right here basically shows what an SVM attempts to do. If you look at the two-dimensional case, say all those data points plotted down there were collected from the switch, within the SVM would try and divide a line between these data points to say, hey, all the green data points are normal data, and the red points happen to be outlier points, which indicate that the switch could be in a state of error. However, if you look on to the third dimensional case, it would then be a plane that cuts the data points in half. So this is why an SVM is super good, because it can scale upwards of 2, 3, 4 n dimensions and try and divide the data in half. Whereas the LSTM, when trying to learn about the trends of data, it looks at these data points in chunks of days over time. So for example, we'll look at 60 days of data points over time and try to see trends of how these data points are approaching the dividing line of whether it's an outlier or normal data. And then so to compare the two models, the two architectures, our support vector machine averaged around 55% accuracy, which is somewhat low, but is definitely a lot better than a 1 out of 15 naive guess because we had 15 labels, which we were trying to predict. And then for the long short-term memory model, it averaged around 95% accuracy, so much better. And while this is a very high accuracy and there are some concerns of overfitting, we are very confident that this LSTM model can be used as a reliable model to notify engineers if the switch is going to enter a state of error.
Yeah, so we use Python to build these models. We use libraries like Pandas, Keras, Scikit-learn, and NumPy. And we also use Python to collect data from Pythos and Paramiko. And other technologies we used included GitHub for version control, Clubhouse for scrum management, and Discord for team communication. Yeah, our achievements include automated the process of data collection from Brocade switches, taking advantage of newer switch technology while supporting older switches, training several classification and trend detection models to predict error states in switches, and establishing the basis for timely notification of engineers about current or developing anomalous situations.
So thank you for listening to our presentation. We're glad to have had you here. Some special acknowledgements is our sponsors at HPE, as well as our professor and TAs at UCSC for their guidance and assistance through these last 2 quarters. So thank you. Here are just some image sources. And if you have any more questions, please do visit us in the poster session. We'd be happy to answer.